So I'm going to share how I prepared the subject in my perspective so that you can incorporate what are the benefits from my point of view and you can prepare it for yourself. So let me share my screen now. Oh, can you see my screen? Can everyone see my screen?
Uh,
Uh,
yeah, visible.
yeah, okay. So let's start the session.
Yeah,
So as
visible.
part of the digital logic
Okay.
subject, we have the following topics to be covered. That is Boolean algebra, the combinational and sequential circuits, number representation. As part of the syllabus from GATE, this is the entire topic. Now we'll see an analysis of what are the questions, like how much marks each and every year it has been asked. Okay, so these are the analysis for the till 2014 have kept it here. So if you see here, it on an average it is asked about 4.5 marks, that is 4 marks, and the topics to cover in this subject is huge actually. So you have to be smart to plan accordingly to give enough number of time. Because it's already September now, so you have to allot only some amount of time. We have other important subjects also apart from digital logic, so you have to be careful not to be what to say, you should not spend more amount of time. You should be smart and see, analyze the papers, like what are the topics mainly they are asking, and you have to prepare it accordingly. And don't be afraid to just rote mug up all the formulas. Okay, sometimes you need to keep those formulas in by heart so that you will be able to solve those questions for easily actually. Because in most of the cases, what they in digital logic, sometimes if they want to ask the question tougher on a digital logic, they will make the questions like difficult, like they will keep for 1 mark question itself, they will keep a flip up conversion or some find the number of states, like that. So if the questions come from the sequential circuit, it will be difficult for you to solve in a faster amount of time. So try to learn shortcuts then and there. Have presented whatever I have jotted down while I am preparing, so you can note it down when and there required. Okay, so according to CS, we have 4.5 marks, and rest of the subjects like COA carries large amount of weightage compared to digital logic. And sometimes the number representation, as I mentioned here, this is asked as part of the COA also. So you should be careful not to like prepare redundantly. So if you're going to prepare digital logic number representation here, then prepare it completely, or else leave it. Don't concentrate number representation in COA, and prepare everything in as part of the digital logic. Don't be redundant again and again. So according now we saw like what are the main topics, and we'll see the subtopics in each and every main topics. So as part of the Boolean algebra, we have the logic gates, the properties, k-maps, canonical form, standard form, minimal expression, and types of implicants. The things I have marked in red are the most repeatedly they are asking. The questions will be based on these things. Apart from these two are not necessary to understand these two, but still the main questions will be asked in k-map, the properties and the types of implicants. And if you consider number system, it's really they touch in every topic as far as there's possible. Okay, so we have to be well and good with all the number system representation. The number system doesn't only cover the conversions from one system to another. We have the floating point representation. They will try to be analytical on that part of floating point. Okay, because these system conversion is comparatively easier compared to floating point number representation. And sometimes the division also, in 2020 they have asked division of two numbers given in a hexadecimal. So we should be well and prepared for the number system topic. And in combinational circuits, we have lot of, as part of what we studied in our UG, we have lot of circuits, but main questions was asked in as part of the gate is like multiplexer and the demultiplexer. Okay. So you should be like last 1 second, sorry. So and if you compare the last question papers, the amount of questions from multiplex and the encoder decoder is comparatively less compared to the number system and Boolean algebra. So you should be well and thorough with these two. Okay, so because these two topics are very easy to score, you can just score 4 marks, like blinking an eye. You can cover these 4 marks, and it will be a game changer if you want to take some high IITs, or like you want to do some government jobs, or anything. The ranking, the 4 marks will be an important game changer for you. So, and that particular game changer subject is our digital logic now. No, and sequential circuits, as I said, sequential circuit is a vast topic. We have lot of things to cover, but make sure that you cover all the topics that has been asked in the gate. Not I have mentioned only from 2014 to 2020, but make sure that before going to the exam, at least once you covered all the question paper from 2000 to 2020, so that you will know a wide variety of questions, what can be asked and which type of questions can be asked, so that you will be prepared for whatever questions that can be asked. There will be a slight changes, that's all. Most of the time the pattern of the questions will be similar. In previous year, if they are asking about find whether for the converting from one decimal to another is, say for example, octal to hexal, then this year they might have asked like some hexal to decimal or something. Like the topics will be similar, but the logic will be different. That is the main key. So the main book to follow is Moody's Mano, but this book I would suggest, if you have vast amount of time, you can follow this book. You can, because this book is really user friendly. I studied from this book actually, but it took me a lot of time. I studied from this book, and apart from that, if if you go to our CS department, I have given a book, last minute notes book that I compiled and made for CS. You can also look for that topic, digital topic. All the topics here covered will be in this book, and apart from that, you have all the subjects covered in this book. So I have given a copy to our CS department. You can go and check it out, and it's also available in Amazon. Okay, so we will see the first topic of digital logic. Digital logic, basic fundas of digital logic is our Boolean algebra. So make sure, like, you obviously everyone will know what is AND gate and what is OR gate. Everyone will know the basics, but the problem is being quick enough to realize this is what is happening in that. Say for example, in realizing an AND realization for a bar, and an AND realization of A and B, A or B. You have to be very quick in saying the formulas. Like it should be in fingertip actually. That is the fact for Boolean algebra. Boolean algebra needs a lot of practice from your end. So we have to remember all these axioms. We have all these axioms as part of the Boolean algebra. You should be thorough, so that if you see most of the time the minimal expression reduction will incur these kind of logics only. Okay, so in that time you should be smart enough to identify this is the law that has been asked here. This is the law, because seeing in two-dimensional or three-dimensional you'll be very comfortable, but if you're given 10 terms, 20 terms, and not 10 terms you'll not get, but at least 6 to 7 terms if you're getting, identifying the what law to apply where will be a difficult one. So you need a lot of practice with these theorems and laws and axioms. So make sure you do that, and I will share this PPT after the session ends, so that you will have a gist down of all the properties, and you can take it for while preparation. Okay, so I hope everyone remember all these laws. We will solve some problems related to this also. We'll know how it is being applied. Okay, so apart from that, we have Boolean function representations. We have some canonical forms. What is our canonical form will be our sum of products and product of sum. all the basics. I hope everyone knows the basics right now. Actually, now what we need to learn is how to smartly solve the problem. That is important. Okay, so I have written all the basics as part of this slide. I think it will be redundant for me to repeat everything because all the basics are being put up directly in the slide. We'll go one by one. This okay. So next is K-map. Apart from what we studied in our syllabus, as part of the syllabus, K-map will be a little bit different as part of the gate solutions. Okay, so what we will directly do is we'll use K-map to directly find the minimal expression. That's it. That's what we have studied for as part of our UG curriculum. But in gate they will drill down K-map in different flavors actually. So this is the four possible implicants. Actually, if you know K-map thoroughly, you will know that each and every term is called as an implicants, and they will ask to count the number of implicants. This such and such implicants are available. So you should be well and aware of these type of implicants. We will see what is these implicants, how we have to identify. Okay, so prime implicant is nothing but all the possible grouping can find it in a K-map. That is the prime implicants. And essential prime implicants is that we have to have at least one that should not be part of another group, so that it appears in our solution. Actually, our essential prime implicant will appear in our solution actually. Okay, but in our redundant prime implicants it will not appear. Okay, so that is the difference between essential and prime. And I know the theory will sound really vague and it will be confusing. We'll see an example for each and every one. And the selective prime implicants is nothing but it's like it, and you can easily remember whether if a K-map doesn't have an essential or a redundant, it will be a selective one. So what will be the selective is choosing one group will make another group to remove from the K-map solution. That kind of possibility is called as a selective prime implicance. We will see that example. So first example, if you see here, I know everyone should know how to map each and every one in the K-map. Okay, so if you map it here and make the possible groupings, you will see these are the groupings available. So number of implicants, prime implicants you will have is this one, this one, this one. So I have marked this A, B, C, D, E. So all these are the prime implicants. Now here there is no redundant and essential implicants. We'll see why. Now if I choose this A, obviously what I will do is it will make B. You will not do B, but you will do this mapping. And if you choose this mapping, obviously you will choose this mapping. So what will be our solution will be? It will be either A, C, and F. So that is one possibility. Now let me do another possibility. Now if we choose this mapping, we chose B. So obviously we will not do this one. We will put this one. We will choose D. And if we choose this one, we will do this mapping. Then it will be E. Depends on what implicant we chose, the solution differs. So hence this is selective implicants. Okay, so that's the difference between the essential and selective implicants. Now we'll see an example for an essential prime implicants now. Okay, so here essential and redundant, this example will cover both the essential and redundant. So as part of the K mapping, what you will do, find the minimal expression. You will map these. First you will try to map the biggest grouping. You will try to do this, but then this will become, this one will be isolated. So we'll try to map these two, but then covering these ones will make sure that these ones are covered. So what makes is, because of grouping this one, it makes this one's redundant to cover. So hence this E grouping becomes a redundant, and the rest of the groups become the essential prime implicants. So I hope until now, looking at these examples, you could easily identify the essential prime implicants, the redundant, and the selective prime implicants. And this is another example. If you see here, this This example contains essential and selective. So I have written the answer here itself. If you see here, choosing A doesn't make like this. You have to choose this one, right? This one is not covered as part of anything. So you have to choose this implicant, but choosing this implicant will ignore this implicant. Choosing B will ignore C, or choosing C will ignore B and will cover as part of this one. Okay, so since this is covered as part of this one, we will make these two as selective. Now we will see here as part of this, choosing C will make this implicant selective, or choosing this one, this mapping will make this one selective. So D will also come as part of the selective, and E, as usual, we can see here this is covered redundant. I mean, this is covered as part of this group, so he will also become selective. So these are the selectives, and this one and this one will become essential. Now we will see some recently asked questions and how to solve each and every one. So first question, we have given a circuit diagram and you have to find the min-terms. So min-terms, we know it is represented by sigma, and max terms is represented by pi. So here they have asked in terms of min-terms. So min-term is nothing but it will be in a product form, and max term it will be in sum form, like this. And min-term represents the 1 and max term represents the zeros. So these are the basics you should know as part of now, but just I'm refreshing as part of these questions. Okay, so we'll try to formulate the expression first for this circuit. So we will have B bar, and we will have B bar C, then A plus B plus B bar C. So here they have asked in terms of min terms. So blindly, if you see min terms in the question, first if you read min terms, and if you get an expression that misses some of the variables, blindly you will just add them. And you should be well and aware how to add all these missing implicants. So if you multiply by, say for example, if B is missing here, you will just add add B and its complement, so that it will become 1. And this is as part of the Boolean algebra properties. If you go there, always the complement and its true nature will add up to 1. So you can add this one. So another C is missing, so we'll add C and C bar as part of this. And as part of this, you will have A and A bar missing. A is missing, so you will add A and A bar, and you have this. So if you distribute all these things, you will have ABC plus AB bar C plus ABC bar plus ABC bar and A bar C B plus AB bar C. So if you see here, this is 7 and this is 1015, 110, this is 6, and this is okay, 1004, and this is 0011 and 1015. So our answer should cover 1 4 1 4 5 6 7. So which would be our option B. Okay, so that is the one simplest form. You can easily score 2 marks for this problem actually. Now, so and if you're given such this like problems from any subject, whatever the subject may be, if you're given a question to find not a valid identity or find the correct one of the following, go always go by choice by elimination. Don't try to do all these stuffs, like don't try to prove everything. You just try to discard this because of so and so reason. Say for example, this you can discard because of associative. This associative property is applicable for our XOR gate. So hence this option is correct. It is not no, it's not a valid identity. It is a valid identity. Now instead of trying to expand this and prove it, let's go skip it because it is large, right? So we'll skip it and go this here. So if you see here, this is also it is trying to, but this is simpler compared to this expansion. So what we'll do is we'll just try to expand. What looking at the XOR gate itself, what you will do, you will try to expand it like this. But if you do it, you will not get anywhere. So you try, if you go to the next option, they have already given another option. But if you remember the Boolean identities, the axioms and the laws, you should have remembered it as XOR is complete NOT of XNOR. So hence you will write it as XY plus XY bar, the whole bar. So that's what they have given here. So this is correct. So now if you substitute 0 here, this term vanishes, and this term, if you bring this complement inside by De Morgan's law, you will get x bar, you will get x bar the whole bar plus y bar the whole bar, which is nothing but x plus y. So these two options is correct. So obviously this is the wrong, invalid identity, and you can just go on selecting it. If you have time, then if you have time, say for example you've completed all the 65 questions, then you need to just make sure this is the wrong answer, you just evaluate and see, you can cross check at the second iteration. Okay, don't do don't do expansion of these terms and the first iteration. Always try to solve the sums. Since you have the ability to go loop around the 65 questions, you can go back and forth, right? So try to go back and forth at least once or twice. First once you just look, this is for solving. First once you just look through all the questions, what are the questions available, and you will be given a paper. Just write down these are the questions you can solve easily by looking at the like just spending some 30 to 45 seconds, you can solve the problem. Write down the question numbers and keep it ready. In the first iteration, just solve these problems alone. If you're not getting anywhere, just circle them and keep it for the second iteration. Do it iteration by iteration so that you will be confident enough, so that you will not just stuck up in one problem. Because the most blunder mistake everyone will make is they will just keep on pondering on one question itself. They will keep on waiting, arriving at a solution, and they will waste 3 to 4 minutes on one solution. They will not arrive anywhere, and they will just keep on. So all these 3 to 4 minutes is wasted on this problem, and you didn't even get the answer. So don't try to do that actually. Now, if we will see another question, which is as part of the Boolean algebra. We have this given. They are given these 4 functions in terms of min terms, and they want to apply this function. They apply this circuit, and we have to find the solution for this in terms of min terms again. So if you're well thorough with your logic, how an AND gate and OR gate everything works, you'll easily go you'll easily go about this question. It is too easy actually, to be fact. What AND gate does, AND gate gives 1 only if both the input are same. That is, 1 and 1 will give 1. Apart from that, everything is 0. So as part of F1 and F2, what are the two things that are same? 2, 8, and 14. These two are the same things. So the output of AND gate will be this min term. Instead of trying to solve this by hands from scratch, be smart actually. Okay, now XOR gate, what will be the output? If the input, both the input are same, it is 0. If different input, then it is 1. So applying that logic here, if you have both the same inputs, that is 2 and 2, you will get 0. So it will not appear in the output. If min terms maps only 1, right? So that's why we are trying to find 1. If it is product, you would have tried to find zeros, but here it is min terms, that is sigma. So we are trying to find only ones. So for 2, it will have 2 here. I'll write it once. 2, 2, 7, 11, 14. So if you see 2, it is found here. So this 2 was already found here. Both are same. So output will be 0. So 2 will not appear in our solution. But if you take 8, it is not here. So 8 should appear in the solution. 14 is found here. So 14 will not appear in the solution. And again, here 2 it is covered. 7 it is not there. So 7 should come in the solution, and 11. So this will be the answer for our circuit. So if you select this, B is the answer. Okay. Now, okay. Now, next question is, they have this. Actually, this is the most trickiest question asked as part of the 2019 paper. Actually, everyone was debating about this question in the forum. Actually, I also wrote it, and I was also making the same mistake for this problem. This problem is the simplest problem they could have asked in 2 marks, and even the question paper setter also thought it in same way, and they gave the first key without revision. The first key they gave the answer what I wrote, and the second they have challenged the key. Some people have challenged the key and they have changed it. Actually, they gave another alternate solution for this, and it became wrong for us. Actually, even the gate question paper setters thought it in the same scenario. We will see what is the problem with this. Okay, so here they have given this function. We have to express in sum of in terms of min terms or everything, and we have to find the minimum number of two input NOR gates to construct this function. So what you'll do as part of the given input itself, what we'll do, we'll try to reduce the expression by constructing a K-map. So if you construct a K-map, your K-map will be here like this. I hope everyone knows how to construct a K-map. So this is the K-map. Now, if you do a mapping, our because our aim is to find the minimal term, we will do a biggest mapping possible. That is this one and this one. So here we have A, B, and C, D, and here you will have C, D bar, and you have C bar. Sorry, C, D. Correct. Sorry, C bar D, C, D, and C, D bar, and A, B bar, bar B, A, B, A, B bar. Okay, so this would yield, this expression would yield common term as B bar and D bar, and this would yield plus BD. Okay, so if you see that obviously it is in the form of X nor Y, that is B X nor of D, and everyone, what they did is everyone kind of mugged up this table. Actually, you will see this table later. Everyone because most of the questions are repeated, as I said, like almost all the questions are repeated as part of the gate. Only thing is they will change the gate or the name and everything. So they mapped all this table beforehand. So I also mapped this table in my mind, so I know if it is NOT gate, you will need one NOR gate and one NAND gate. If it is AND gate, we will require two and two for NAND construction realization, and three for NOR realization, and so on and so forth. So by looking at this table, if you see for XNOR we had four, we need four, so we all wrote it as four, and thank God it was a numerical type, so we didn't had any negative marking, but everyone wrote as 4. But there is actually another point we forgot to read. Here they have given that all the complements were available already. So if you do that, if you try to utilize that as here, if you take B bar and D bar and realize the gates, and B D bar to realize the gates, you can construct this XNOR within 3 NOR gates actually. If you do here B plus D, B bar plus D bar plus B plus D bar, the whole bar. So if you pull it out here, we have B bar plus D into B plus D bar, which is nothing but if you pull it out, I mean, if you distribute it, you will have B bar plus D bar, which is our required thing. So the exact correct answer was 3, and because of this row table, we wrote as we took it as 4. In this table, actually, what is assumed is if every possible terms, even A bar, everything has to be A bar, B bar, everything has to be constructed from scratch. Hence, that's why it is requiring 4. But here they have given complements are available already with us. So the major mistake you should not do is try not to be happy with the questions, saying that it is already, it's known for you, and you should not ignore the questions. You should read the question completely before answering. So that is also important. And the answer is, of course, it is 3. Now, next question is, they have given this this expression, saying how to find the incorrect one. So And as I said, if you're strong with your axioms, you'll obviously see this is correct, this is correct, this is correct. But if you're not, you have to expand it actually. This everyone would have, eliminate it. So this is the easiest option. But this one you should you would try to expand it actually. P bar is P bar Q bar plus P double bar Q, which is nothing but P bar Q bar plus PQ. So you will try to, so this time expansion time is wasted. But if you go to our axioms here, we have this axioms. If you remember this axioms, and this comes only with practicing many number of times. Only you will try to remember all these things. So if you remember all these things, you can easily eliminate this option. You can eliminate all these option and this option, and you would actually find this is the wrong answer actually. Okay, let's try this one. So P bar plus P bar, sorry, P double bar, P bar, P bar, whole XOR of Q. It is nothing but P into P plus P bar. P plus P bar is 1 XOR Q, which is nothing but 1 Q bar plus 0 Q. Right? Yeah. So which is nothing but Q bar. But if you expand P, this one, you will get P bar plus P bar P double bar, which is nothing but P bar into P bar. It is 0 whole XOR of Q bar, which is nothing but Q 0 into Q bar plus 0 bar Q bar double bar, which is Q, which this is 1. So the answer will be Q. So this is not same, and hence this is the invalid identity. Now next question, this is similar. Again, we are given this Boolean function, and we have to find the number of essential prime implicants. This question is direct actually, but they gave this word terms to confuse you actually. Essential prime implicants, nothing but whatever the solution, whatever the terms that comes as part of the solution is our essential prime implicants. So if you construct a K-map for this, you will get 0, 1, and here you will get 1, don't care, and then 1, 1, don't care, 1, don't care, don't care, and don't care. So this is the K-map for this one, and we will try to map the essential prime implicants here. So if you try to map the K-map for a minimal expression, what you will do, you will try to map these things, and what you will map these corners. So your number of prime, or the number of terms in your K-map will be 3. So answer is 3. Now we know EPI is pretty straightforward. We will find the number of redundant and selective prime implicants, whether it's present here or not. Okay, so I will construct the K-map again with another box. Okay, 1, 1, don't care, 1, 1, don't care, don't care, don't care, 1, 1, don't care. Okay, so now if you try to map it, first we will try to find all the possible prime implicants. So this is one prime implicant, and if you do, this one will be one prime implicant, and this this one and this one you will try to map it as a prime implicant, and this one and this one you will try to map it as a prime implicant, and all the corners you will try to map it as a prime implicant. Okay, so there are okay, so there are, this is one implicant A, and because this corner is B, and this corner is C, and this is D, this big grouping is E, and this is F. So there are 6 prime implicants. Now we will find, we know whether there are three essential implicants. What are the essential implicants? Essential EPIs. I will write it here. EPIs are, we have A and this grouping D and this big grouping which is named as E. So these are the essential prime implicants and redundant prime implicants. Can anyone find the redundant prime implicants here? Can anyone answer? Is anyone there? Or it is confusing? Should I repeat again how to find the redundant prime implicants? I think no one is there. Okay, so if you see here, the redundant prime implicant here is this F, because covering E and covering F is redundant, because as part of E itself you will cover this F. So covering F separately is redundant for us. Okay, now can anyone find another, if you don't need to answer, at least for your sake try to find it another two prime implicants. There are another two prime implicants. One redundant prime implicants. The two other things are this corner two mappings, that is B and C, because as part of A there's four corner mapping, this big mapping, four group mapping. We are covering both C and D separately. These two group mappings, B and C are two group mapping, but A is four group mapping. So as part of this four group mapping, we are covering these two group mapping. So B and C are redundant here, and there is no selective, because choosing this does not eliminate any other grouping. Hence, there is no selective implicants. Yeah, so answer is 3 as part of the prime implicants. Now, the number system, everyone knows how to convert from one number system to another. So we know if you're given a decimal number, if you want to convert it to binary, you will just divide it by 2. If you want to convert it to octal, you will divide it by 8. If you want to convert it to hexa, you will divide it by 16. If you want to revert it back, multiply by 2, this is multiplied by 8, and this is multiplied by 16 with respect to the bit position, that is 16 power I. The bit position of the bit MSB and LSB matters. And if you want to convert across these, that is binary to octal, you do three grouping, and if you want to convert to hexa, you'll do 4 grouping. Okay, and if that is if you have, say for example, 0 0 0 0 1 1 1 0 1 0 now 1. Okay, now if you want to convert to an octal mapping, I mean octal numbers, what you'll do is you'll put you'll put groups of 3 and you'll just try to write the solution 0 0 7 4 5. This is the octal base 8. Now if you want to do a hexadecimal, what you'll do, you will just perform a group of 4. Okay, 1 2 3 4 1 2 3 1 2 3 4 1 2 3 4. So we have 0 1. I think I mapped extra here. 1 2 3 4. Sorry. So this is 8 4 2 1 10 14. 14 is E. A, C, yes, E, and then we have 5. So that's how you convert binary to hexa, and if you want to revert it back, you'll just expand these terms accordingly. If it is, they are asking 16-bit, you'll just add extra 2 zeros or something like that. Okay, so this conversion part is very easy, but the IEEE that is floating point representation part is what that makes the number system little bit tedious actually. So we'll see, this is the IEEE representation as part of like all the as part of like what to say, COA itself. You will get all these things, but in digital logic you will not have a separate dedicated chapter for this IEEE notations. So first notation, you will have this. First you will have 1 bit for sine, then you will have 23 bit for mantissa. We will see what is mantissa, and we will have an 8 bit for our exponent, and we have a 16-bit representation as similar so and so. But while writing in while storing in computer, what you'll try to do is you'll try to find this exponent uh, which is additive of 127. Whatever we get, you'll just add 127 and you'll try to store it. That has a specific advantage. We don't want to dig deep on that, but we'll try to represent as part of this format. So for the 32-bit, you'll have this format, and 16-bit you have to remember this format. Okay, we'll see one question before we'll move on to our next topic. Okay. So this is the recent question I have said, like how to solve. They are given two registers, and these are the values that is contained as part of the registers. We have to find the answer for this division. Okay, so how you will find that is the, if you try to convert and do, it will take a lot of time to do that. So we'll try to do it in a smarter way. Okay, if you know, these are whatever it is called as the IEEE representation we saw before, right? These are the IEEE representation. If you convert to plain, if you multiply by 16 power 1, 16 power 2, it will not work out. So you should be careful, because here they have written it as single precision floating point numbers representation. This is not simple decimal numbers, that is base 10 numbers. These are decimal numbers. So we have to find the solution for this one. So we'll try to write this, expand this, and you'll find out. So first, and I'm ignoring all these zeros here. So if you see here, this is the major term. Now if you try to expand it in terms of binary, you will get 0 1 0 0 0 1 0 1 0 0 1 0 1 0, and rest of our zeros divided by 1 1 0 0 0 0 0 1 and 0 0 1 0. Okay, now from previous slide we know 1 bit is allocated for sine, 23 for mantissa, and 8 is for exponent. Exponent is always in the middle. We have to remember this format also. This is the representation, this is the bit format. So the first bit here, represents the sign, and then we have 8 bits, 1 2 3 4 5 6 7 8 8 bits for the exponent, and then this is mantissa. Mantissa is nothing but the fractional part. Okay, so the fractional part is here. You can see that the fractional part is same, so obviously they'll get cancelled and it will be 1.0000. Okay, so there is no fractional part. Now we have to find the exponent part. That is the problem. And if you see here, the sign bit is 0 here, so hence it is plus, and it is 1 here, so hence it is minus. Okay, so obviously our answer is minus. That is the that is -1 the whole power 1. So sign bit is 1 in our solution. Now we have to find the exponent part. Exponent part, if you see here, if you solve this, this is 1 2 4 8 16 32 64 128. Okay, so 128 plus 4 132. 132 divided by 128 plus 2 130. You should not divide, because this is exponent. What, as part of the mathematics itself, what you'll do, if you have some 2 power 10, 2 power 2 12 divided by 2 power 10, what you'll do, you'll subtract the exponents, right? So same logic applies here. So 2 power 2, you'll have, this is 2, but whatever the exponent here what you are getting is, it is nothing but exponent minus 127, it's 2. So what you have to do, what the representation, IEEE representation, we have to add 127, so it will become 129, which is nothing but the first bit and the last bit will be set to 1 1 0 0, and we have 0 0 0 0 and 1. Okay, and the rest of the mantissa is 0 for us because it is same, right? So, and if you see here, it is 1 dot mantissa. Mantissa will be 0 always. This is implicit 1. There is another format called as explicit and implicit. Implicit is representing that 1 here. Explicit is 1. It will always assume the first, that mean, what to say, the digit before the point is always 1. Implicit is, we will say it is 1. You have to store this 1 separately in our system. In explicit, it will assume that it is always 1 and it will not store it. That is the difference between the implicit and explicit representation. Okay. So here it is, we have everything as 0. So in this matrix part will be 0. So if you try to form the solution, this is C and this is 0, and the rest of this will be 4 groups will become 8 and rest will be 0. So answer will be C08 and rest will be 0. So D is the correct answer. Okay. So, and again we have and as part of the number system, complements also covers. So I hope this and all, it's like it will be refreshing after writing complex question. This and all will be refreshing for you. You just have do a long division and you will just find whether the find the binary representation of this. So you will have 1 1 1 0 0. Okay, and it is saying to represent in 16 bits. So we have all 4 here, 4. Then we need these 2 and okay. So what is the procedure of the 2's complement? We have to invert all the bits, then add 1. So inverting all the bits and adding 1, which is 0 0 1 0. Okay, I think rest of the thing will be same. So we have to see last 4 bits as 0 1 0. So these last 4 is 0 1 0 and the rest of the things is 1 1 0 0 1. So if you see here 1 0 0 1 0 1 0. So this is the answer. So C is the answer. Okay, and next question is given consider z is equal to x minus y, x y z are sign magnitude, x and y each are represented with n bits. To avoid overflow, what should be the minimum minimum requirement for z? So obvious by looking at it, overflow situation itself, you should note this at least 1 bit we require, because overflow occurs because of this extra, that is carry. Say for example here, adding 1 plus 1, we will have at least 1 bit as part of the addition, or subtraction you will just need to borrow 1 bit from somewhere. So that kind of that extra 1 bit, at least 1 bit is required for the result to avoid overflow. So n plus 1 bits will be required here. Now, another question is, they have given a custom representation format, and we have to find in this representation format which of these following cannot be represented. So if you see here, a smart decision you do is not trying to convert the numeric, the whole part of this number, because they are given 1 2 3 4 5 bits for the non-decimal part, that is before the left side of the decimal system. So if you have 5 bits, obviously you can represent some 0 to 31. So obviously all of this numerical, the base 10 part will be representable. We have to find only the decimal part of this. So don't try wasting time in converting all this, because they are not writing anonymous paper. So try smart in solving all this. So first, if you take 1, how will you convert? You'll just multiply it by 2. So you will have 1.00 and you will have 00 into 2, which is nothing but 0. So obviously you can represent some part for 31, and then you'll have 100. You can represent 1. Now if you have 0.875 into 2, 1 second, I have to take my calculator. 0.875 into 2 is 1.75, and then 0.75 into 2 will become 1.5, and then 0.5 into 2 will become 1.0. So and then we'll have 0 into 2. So obviously it will become 0. So hence we can represent within the 3 stipulated bits, that is 0.111, it will represent. So this is also, it is representable. Now we'll see 0.100 here, something. sorry, this is A1, this is 2, this is 3. Okay, so 0.100 into 2, which is 0.2, and then 0.2 into 2 is 0.4, 0.4 into 2 is 0.8. So what it will become, we have only 3 bits. So some for 12 we will have some kind of bits, and then for 0.100 we have only 000. But if you revert it back, we will have only 0. So even though our intention was to represent 12.1, but we can represent only 12.0. So hence this is not representable. Similarly, if we try this for this one also, you'll end up with the same scenario. You'll get 000. So this one and this one is not represented. So hence C is the answer here. Okay. So let's go to the next one. If you see here, this one is simple, I guess. You just find the number of possible combination answers for this one. What we'll do is we'll expand it as, because 4 in, say for example 43, how we'll write in base 10, 4 into 10 plus 3. So in same scenario I'm writing here. So on y is 8y plus 3, which is nothing but x is 2y. So and we can see here at least 3 and 4 is here. So x should be at least greater than equal to 5. If it is base 5, 0, 1, 2, 3, 4 will be there. If it is base 6, then also it is possible, but it cannot be less than 5. And here it is saying y is less than 8. Less than 8. Okay, so so if you try that 1, 0, 1, 2 for up to etc for 7, you will see that till 2y here it will be x is 2y, right? So 2y, if you see 4 till 0, 1, 2, you will not be able to represent. 4, 5, 6, 3, 4, 5, 6, 7, you will be able to represent all these x equal to 2y. It will be, I mean, the condition here will be satisfied. That is, here it will 6, 8, 10, 12 and 14, which is all greater than, apart from this one is greater than 5. So obviously there are 5 possible solutions for this one. Okay, next we have, as I said before, this is the table. You should have it in your mind. Don't try constructing this table on spot in the examination, because it will require a lot of time to find whether this is the number, this is exact answer or not. So try to remember these tables, like it should be remembered as part of the it's like number tables. You have to 12 table, 10 table, like that. You have to remember this realization table. Okay, so apart from this, we have all these formulas that has been asked as part of the previous gate. You can have a look after sharing the PPT. I'll share the PPT. And as I said, this topic mainly they look on for multiplexer and encoder. Okay, so and that too they'll be having only the basic questions. So don't look at the problem. It will be big for multiplexer questions. It will be big. They will give circuit diagrams or something like that. Try solving these questions. But if you're not reaching any solution, just keep on. These solutions sometimes will be tricky actually, and this one particular, this conversion will be the most trickiest one. And if you apply this formula, say for example, if you want to convert a 64, you have to have a 64 cross 1 marks to a 4 cross 1 marks. What you'll do is you will do 64 by 4, which is 16. Then you will do 16 plus by 4, which is 4, and 4 by 4, which is 1. So number of marks required is addition of this. Okay, so which is nothing but you need 21 4 cross 1 marks to emulate the 64 cross 1 marks. So that is the formula here it is represent. Okay, so we'll see some questions related to this. Now, in this question, they have given that there are 32 registers and there has to be mapped to a accumulator. So 32 register is mapped to one accumulator, one accumulator. So obviously they are given a 2 power n mux, and you have to find the number of select lines here. So obviously you have to find the n. Mux is nothing but we have 2 power n input and 1 output. Given that we have n select lines, so we have to find the n. N is nothing but here 5. And be really good with your powers of 2. So you should be really good with powers of 2. If you ask 2 power 10 is 1k, and 2 power 20 is 1m, 2 power 30 is 1g. You should be really good with the powers of 2. Now here if you see here, they are given a decoder. So for decoder, what is the format of the decoder is, so we have 2 power n, given n lines, you have 2 power n output lines. So here they have given m input lines and n output lines. They are going to address 1 kb of RAM. So our output is 1 kb of addresses we have. So there is 1 kb is 2 power 10, just now we saw. And we have to find the m plus n. So yeah, n is nothing but we need 10, at least 10 address lines to map the 2 power 10 addresses. So they are asking to add m plus n. So m plus n is 10 plus 1024, which is nothing but 1034. Okay. Now the second, this question, it is that's what I have said before, right? The questions from this combinational circuits are really very, what to say, limited actually. In 2020 only they have asked it. Before that, in 2016 only the marks and all had appeared actually. But it is safe for side to know how to solve, because these are really simple to solve. You can, if you know the logic how to solve it, it is really simple actually. So they want to find the output, that is minimums, the expression for this mux. Okay, how you'll write the output for a single mux is you will just take this, what is the variable around here in the select line. You have two options for this one. Say for example, this is p bar, this is 0 or 1, that is p bar or p. Now if it is 0, it will select this one. If it is 1, it will select this one. So p bar into 0 plus p into r. Okay, that will be the output of first mux. Okay, second mux, the first mux is input, and the second we have the select line. So what you will do, you will put q bar into r bar plus, you will have the entire thing, p bar 0 plus pr into q. If you solve it, you will get q bar r bar plus, this will vanish, and pqr, which is our option D. Okay, now we'll see this question. Same, instead of one input, we have two select lines, right? So we'll have p bar, q bar, and everything. So we'll have p bar, q bar, p bar, q, p q bar, p q. So if you multiply, this will vanish. You'll have p bar q plus pq bar plus pq bar r plus pq r bar. So if you see here, the option doesn't have this one. If you are well and thorough with identities from Boolean algebra, you can just directly find out the law of absorption here. Okay, if you're not very good with it, try to do it in a K-map, simple, fast as possible. Okay, if you see here, if you try to expand this term, you will have p bar q r plus p q r bar. Okay, that is adding and adding r and r its complement to express in min term format. Okay, so what you will get is 0 1 1 1 0 1. If you draw a K map, okay, if you have draw a K map, you'll have 5 7 6. Okay, then you will have 1 here, and 1 0 1, which is 5. Sorry, this is 1 0 1, this is 0 1 0, which is 3 2, and this is 1 1 0, which is 1. So if you try to solve this one, you will get, if you put p and qr, p, this is q bar r, qr, qr bar, q bar r bar. Okay, so if you try this mapping, you will get p q bar r, and then you will have p bar q plus qr bar, which is our first option. Okay, so don't, if you're not able to solve it with Boolean algebra, you're not very good with Boolean algebra for axioms, try to convert it to a min-term format and just do a K-map. It is simple, but this works only if it is 4 variable or 3 variable, it will be easier. But if you're going beyond that, you should really have some grasp of the Boolean algebra axioms, so that it will be simpler to solve. Okay, so answer is A. Now again, if you see here, the same problem. If you see this one, p q bar r, same kind of problem. We'll have this one plus p q bar r bar plus p q r. if you try to map this, it will be same in the K-map. In such cases, you should be very careful because if you do a K-map mapping, you will get the same terms again, because K-map will not convert XORs and XNORs. So you should always be try to identify all these ones. If you take these common plus PQ bar plus PQ bar whole bar. Or if you see here, this is complement of this one and this is complement of this one, obviously. So hence it is P, Q, X or R. This is the answer. Okay. Now, next we have the sequential circuits. On sequential circuit, as I've said before, majorly they will ask questions related to number of states and what is the sequence of the outputs and everything. So here we have listed some important formulas. You can go through later. We'll solve some sums and make sure you remember, like, you should be very good with this transition table if you are going to attend the sequential circuit, because constructing the transition table again there, it will be difficult for you. Okay, now let's try to solve the sequential sums. Okay, here they have given two flip-flops that has been arranged in sequentially, and we have to find the output for this one, and we have to find number of transition back. That is, this one they are asking is number of states that have self loop. That is being asked. What is the transition table of D flip-flop is? If you have Q and D, if it is 0, our D will be 0. If you're sorry, I think I reversed it. Qn plus 1. Okay, if the 0, 0, 1, 1, 0, 1, 1. Okay, if the previous state has 0, this will be 0, and if D has to be set, it will be 1. And if previous, irrespective of the previous state, if it is 0, it will set to next state is 0, and if it is irrespective of the previous state, it is set to 1, it is 1. That is, if D is 0, we'll just set to 0, and if it is 1, you will set to 1. That is the D flip-flop transition table. Okay, now what you have to find is a number of states that have the self loop. We have to find that one. So for that, we have to construct the transition table for this entire flip-flop. So we'll try that one by one. For the first, we have the input, then we have the Q0, Q1, and the output of the flip-flop. This D will be input, and D1 is D0, and the next state here. Okay, this is current and this is next. Okay, now if you try to do this, if you do 0, 0, 0, 0, 1, 0, 1, 0, 0, 1. Similarly, if you go down here, you will construct a table. Now, if you remember the table, I mean our D flip-flop transition table, you will easily fill this table, this particular table actually. So what will be the output? D in will be D. I mean input of this will be D0 and this will be D1. This is Q0. This is Q1. Our D0 will be input. Okay. Just whatever input will come here. So 0, 0, 0, 0, 1, 1, 1, 1, 1 will come here. And what is our D1? D1 is nothing but our D0. What is the D0? D0 can be the that is current state of the first flip-flop. That is, D1 has the input of the current state from the previous flip-flop. So this should be mapped for this one. That is the only trick you have to remember. So it will have 0, 1, 1, the same things, same whatever bits available here will come here. And if you fill here, it will have 0, 0, 0, 1, 0. If you try this one, you will easily fill this table. So now what they are asking is, you have to construct this table, then you have to find number of table we have the self loop. So if you see here, this is the current state and this is the next state. Okay. So from 0, 0, 0, it's again going to 0, 0, 0, given 0 and 0. Okay. And from 0, 1, it's going to 0, 0, 0. Sorry. So from 0, 1, it is going to 0. So on 0, 0. Similarly, if you construct all the tables, you will find that two states will have the self loop. Okay, so the answer is 2, I guess. Yeah. So answer is 2. Two states will have the same self loop in the state transition diagram. Okay. So constructing this for 1 mark is, I would say, is really if you have enough number of time, you can do this, but constructing this table itself will take at least 2 to 3 minutes for you to do this, and converting to state transition and then seeing us almost 4 minutes you will waste it for 1 mark. So better try this question at last. So that is being smart here. Okay, now and again we have this another question from previous it's long back. So if you see here, the transition, you have to find number of flip-flops required. So if you see the points to remember, you will see that if you have n flip-flop, you will have n 2 power n states, and if you have n bits, you require n flip-flops. Okay, and if you given number of states, given a number of states, you have to at least have log number of states of flip-flops. Okay, so looking at that one, we will see that number of states as 0, 1, 2, 3, 4 states. So we'll blindly write the answer as 2. But there is a trick here. There is a two. We'll try to construct this transition table without knowing the JK flip flop itself. We can construct the table by looking at it. Okay. First, from 0 we are moving to 1, and from 1 we are moving to 0, and from 0 we are moving to 2, but already the entry of the JK flip-flop has 0 to 1. So this is not possible to do. Again, it will go to this one. So we need an extra one more state actually to represent this particular 0. So we have 1 0 that represent a transition to 1, and another 0 that represent a transition to 2. Similarly, from 2 to 0, and this 0 from transition to 3. Okay, so we have 3 different kinds of zeros. So for these 3 different kinds of zero, we have 3 extra. I mean, for 0 we have 3 states, and apart from that we have 3 states. So the answer is 6 states. So log 6 ceiling. I mean, we'll have ceiling actually. We'll have some 2 point something, or we need at least 3 flip flops to do this. Okay, but it is at least 3 flip flops. But to be exact, actually, the question answer for here required. They have given a variation. Using this logic, if you answer 3, this is also correct, but to find the exact number of flip-flops required, you need, because this is 3 kinds of 0, right? So first, for 0, for the first 0, for transition of 0 to 1, we will write as 0 1 0. For transition of 2, we will write 0 1 0 0, and transition of 3 will write 1 1 0 0. And for each and every transition, we will have 0 1 1 0 1 1. This will be 0. Okay, we don't have different types of 1 and different types of 2. So we need at least 4 bits to represent these states. So to be exact, we need four flip-flops to represent the this particular sequence counter. So answer is, they have accepted both 3 and 4 for this problem. Okay, and Johnson counter, we know Johnson counter, simply will have all the counters interconnected, and the last counter will just invert it and you'll just feed it back. So they gave the initial value as 0 0 0. So what you'll do, it'll invert it back and you'll feed it. You'll have 0 0 1, and everything will be given 1 1 0 0, 1 1 1 0, 1 1 1 1, 0 0 0 1 1 1, 0 0 1 1, 0 0 0 1, 0 0 0 0. So again we reach the initial value. So it is 0 8 12. So we can see this is the sequence here. So this is the answer. Okay. So these are the possible questions we covered as part of the digital logic. Okay. So you can see that there is a lot of topics to cover. There is a variety of topics, but if the logic, if you have enough number of practice, you can solve it easily. But sometimes it requires a lot of computation time also. Say for example, our D flip-flop case, we require a lot of time for 1 mark itself. So in that scenario, be smart to attend only the questions that are solvable as part of the first iteration, then try to solve these type of questions as part of the second iteration, so that your aim is to score maximum number of marks. Your aim is not to show that you have the knowledge, because they don't know whether you have the knowledge or not. All they see is whether the answer is correct or not. So they're trying to do this a problem for 1 mark is waste of time, the D flip-flop. So it's better to ignore some of the problems. Some problems will be given in such a way that it will make sure that it will take your time to finish that problem. So be smart in avoiding such problems. I hope this I think I have covered all the topics as part of the digital logic. I will share you the PPT to Karthikeyan sir, and he will share it with you. Okay, thank you. Sir?
Yeah.